My name is Moraru. I'm a professor in the Department of Food Science at Cornell, and I would like to present to you a brief video report of our project Microwave Vacuum Dehydrated Shelf-Stable Cream. The main goal of this project was to develop a method to manufacture a novel shelf-stable cream product using a process that allows the dehydrated cream to be reconstituted with minimal effort and energy, as well as retain the functionality of the initial cream. One of the motivators for our project was the booming global market for cream. It has been recently estimated that in the US alone, the market for cream will reach over $19 billion by 2027 at an annual growth rate of about 3.8%. Within the larger cream category, thickened cream and whipping cream have even a higher growth rate of 4.3% by 2027. Nonetheless, there are some challenges for this whipping cream category in particular. If you look on the left-hand side in this graph, we can see that there is a strong competition for non-dairy cream products. While the dairy cream has quite a good growth rate, the non-dairy alternatives grow even at a faster rate. On the other hand, within the dairy category itself, consumers prefer fresh cream products without preservatives, which are the ones that drive offline sales, like in stores and supermarkets. But we do live in an era of online sales, and even for cream, they are anticipated to grow at 8.5% annual rate, which is double the growth rate for the entire category. So that simply suggests that there is both an opportunity and a need for innovation in the shelf-stable but preservative-free category. If we are able to create a shelf-stable cream product, this will also open tremendous opportunities for export from New York State and the United States in other parts of the world. So the key questions that our project addressed were the following. First of all, how can we create a product that is shelf-stable, has high quality, while it preserves and adds value to the cream? And the second part is, how can this product be easily reconstituted and converted to whipped cream and butter, for example, with minimal effort and energy? Let's talk first about creating a shelf-stable product. The requirement for a shelf-stable product is to prevent chemical and microbiological degradation. That is typically achieved when you have a very low moisture content. And that low moisture content would prevent browning, would prevent lipid oxidation, and would also prevent growth by bacteria, yeast, and mold. For cream, as for other dairy powders, the required moisture content for this stability to be achieved is to have less than 1.5% water, which corresponds to water activity below 0.3. And to achieve this, we identified a process that is uniquely suited to do that, that is microwave vacuum drying. We explained how this process works, both theoretically and practically, in our previous reports as well as in our proposal. But I just want to remind you that this process combines the ability of microwaves to heat up and dry the product fast with the ability of vacuum to lower the boiling point of water, which allows drying at a much lower temperature than regular drying processes. We also learned during the previous reporting period that it is important to homogenize the cream before drying, because that allows the product to dry uniformly and to produce a product that is not separating during the reconstitution. And at that time, we presented to you how important the homogenization is and what are the values of pressure that can be used for that. I want to emphasize that this homogenization would be done in a regular milk homogenizer that's present in any dairy plant. We also discovered that there is an ideal fat content for the initial cream, because if we have too high a fat content, that would create a product that's excessively thick, and that will slow down drying and will increase the energy demand for drying. During the last reporting period, we focused a lot on the structure of the fat inside the microwave vacuum dried product. So we looked at the fat globule size and structure in various ways. If we take a look at the images on this slide, where we used a special microscopic technique that allows us to see the fat globules in red and the protein in green, we can see on the top panel that fat is present in these relatively large fat globules, somewhat separated from the protein, which is shown in green. In the middle panel, you won't see this clear separation of the colors, and this is because after homogenization, the fat will be present as tiny globules that are surrounded by the green layer of protein, so you don't see these layers as clearly separated. However, after the cream has been homogenized, microwave vacuum dried, and reconstituted, we see again a structure that is reminiscent of the initial cream, and you see here portions of red that represent fat globules that are very similar to the top image that shows the initial cream. They are somewhat larger in size, but otherwise they are very similar to the initial fat globules. Something else that we looked at is the layer that covers these fat globules. When milk fat is secreted in the secretory cell by the cow, the fat globule is covered by a very complex membrane that has a lot of chemical compounds, but I want to bring your attention to one single class, phospholipids, that are extremely important molecules for the functionality of these fat globules. In the panel on the left-hand side, you can see a schematic diagram of this membrane of the fat globules, and phospholipids are represented there by this symbol that looks like a black light match. So we were able to dye these phospholipids and look at them under the microscope, and you see in the middle panels these fat globules covered in a purple color layer, which represents phospholipids. Again, just bringing your attention to the top and bottom panels, the structure of these fat globules, again, are very similar before the process and after the vacuum drying and reconstitution. And the phospholipids are also present at that interface at the surface of the fat globules, very similar to the way in which they show in the original cream. These similarities will also suggest that the similarity in functionality will also be there. And just focus in this report on one single functionality, and that's the whipping behavior. We all love whipped cream. I love whipped cream myself. So what we did was to reconstitute cream using water from the microwave vacuum dried powder and whipped it. This is something that the consumer can do in their home, and that is one of the final possible utilizations for the product that we're developing. We looked at the stiffness of the whipped cream, which is a very important characteristic, using an instrument called a texture analyzer with a special attachment. and we measured the stiffness. And if we look at the panel in the middle that shows a graph of stiffness as a function of whipping time, you'll notice that for the initial cream that shows here in green color, the peak stiffness is reached at the level where that green arrow is somewhat comparable to the peak stiffness, that we obtained for the microwave vacuum dried reconstituted whipped cream. Indeed, for the reconstituted product, the stiffness was just a little bit lower, but this is also because the fat content of that cream was lower. It also required a slightly longer whipping time, but not excessively long. So this is something that would lead to an acceptable result from a user's perspective. So just to summarize, we feel that we've been successful on all of the components of our project goal, which were to develop a method for manufacturing of novel shelf-stable cream product using a process that allows the final product to be reconstituted with minimal effort and energy, as well as retain the functionality of the initial cream. What's left in the project is to look at how the product behaves over time during storage. So we are currently conducting a shelf life study to particularly look at lipid oxidation and color, which could be the two modes of failure for the final product. I am also happy to report that we did file a patent disclosure, and we're hoping to be able to patent this process and product that will bring it one step closer to its commercial utilization. With that, I would like to thank you for your support of this project, and I would like to acknowledge the assistance from Michael, who is the undergrad working on this project, who learned a lot about dairy products and dairy product characterization while doing this work, along with Josef Dumpler, who has been responsible for all the work in the project, and he is now working in Switzerland.